So thank you everybody for attending our optimization lecture. We are going through a book called Numerical Optimization by Nocedal and Wright. So let me write that out. So here we have Numerical Optimization by Nocedal and Wright. So we're going to do just chapter 1 today, which is the intro to optimization, but it gives a good high-level overview of what's going to come. So the first thing is that when you have an optimization problem, the goal is to try to make something the best it can be or the worst, depending if your optimizing is minimization or maximization. And so here we have some components of that. So when you want to make something the best or the worst it can be, first you have to define what's your metric that you're trying to make as good or as bad as it can be. That's called the objective function. And so because I'm going through this book, I'm going to use some of their terminology. It's a quantitative measure of the performance of the system under study. And then there's to make something as good or as bad as it can be. So like, let's say that's something like 2x1 plus 3x2. So this can be like some measure. Maybe this is like a price per unit or something, and this is the number of units or something like that. That can be the idea, like this is some type of profit now. So this is something someone might want to optimize. And so in order to be able to optimize something, you have to have some variables that are what we call decision variables. I didn't see the decision in this book used, so people might have slightly different ways of calling terms. I think in this book they were just calling it variables. Generally I see the word decision variables. But so then to optimize a function, you need to have something you can actually vary. So if I just give you this function, I tell you, well, make this as good or as bad as it can be, but x1 is 3 and x2 is 5. Then it's like, okay, well, I don't have anything to optimize, right? You just told me here's what the number is. So you actually have to have decision variables, things that you can change in order to optimize your function. And a lot of times these might be constrained. So you might be able to like optimize x1 and x2, but not infinitely, right? So even if we're going again with the price and the unit thing, if this is profit and I say make this as big as possible, it's like, okay, well, then I'm going to sell an infinite number of units. And it's like, okay, that's impossible. You're not going to be able to do that. So probably you have something that says like maximize the profit subject to you can only make like so many in a month. Like, oh, okay, it has to be less than 5, but greater than 3 or something. Like I have to at least make 3 this month, but no more than 5, maximize my profits or whatever. So you can already see that this is going toward like, if we had the same thing for x2 and it was between negative, oh, I guess I wouldn't have that, 0 and 1, that then to maximize this, I'm going to choose x1 as 5 and I'm going to choose x2 as 1. So I'll just choose it because I can already see that that's the way to make this as big as possible to essentially go to the bound of the constraints. But it's not always true that you operate at the bounds of your constraints. So you have decision variables, and then the decision variables could be constrained. Generally, we call things like this bounds in like actual optimization software, and then they'll call other things constraints in the software. But I think from a theoretical perspective, these are constraints on your variables. We're going to talk a lot about the different things related to both theory and then algorithms. So there's always a theoretical way of understanding these things where you say like, okay, what is my problem? How do I model my problem? So when people write optimization problems for a physical statement, that can be called modeling. It's different than what we typically think of as modeling in chemical engineering, where we think of as modeling more like modeling your, you know, like a chemical process, but like through differential equations. But here in optimization, if someone is an optimization expert and they're going to do modeling, what they might mean is they might mean taking a statement of what needs to be optimized and what the constraints are and transforming it into a mathematical representation like this. So there are many different types of algorithms for solving these problems. And so there's going to be theory for optimization that then leads to algorithms for trying to solve the problems. Algorithms, there's not only one algorithm. That would be really nice if it was that easy, where there was only one way to do optimization and you always did it the same way. Unfortunately, optimization also involves a lot of art, in that there's actually a lot of algorithms. Usually the person trying to solve the optimization problem is responsible for selecting a good algorithm for their purpose. And the selection of the algorithm can actually be very important. It can change whether or not the problem is solved at all, whether it's solved fast, or whether it's solved slow. And when we say, does it get to a solution, we mean like not necessarily even the question of does the actual original problem have a solution. That's important. But even whether or not, even the original one might have a solution and the algorithm can't find it. So that's also an issue. So the way that then you need to like have an algorithm that tries to find the solution, and then you have to have a way of knowing whether it did or it didn't. And the question of did it or did it not find a solution is in many ways based on theory. So there's these things called optimality conditions, and we'll talk more about those in the coming weeks, but those are used to determine whether or not you actually found a solution to the optimization problem. And so a model can be improved by things like sensitivity analysis that show how sensitive the solution of the optimization problem is if you change your model or you change your data. And optimization is going to be minimization or maximization of a function subject to constraints on its variables. And so I would say that that is what we do in our group with control, is we work on optimization-based control, and optimization is minimization or maximization of a function subject to constraints on its variables. And so X is going to be our vector of unknowns or decision variables. This is a little bit confusing, I think, to remember, and this is often it will be called X even in some of the optimization software we're going to use. So just an important distinction from nonlinear systems theory to optimization is that just to be clear on what your thing means at any given time. So if you're looking at an optimization problem and someone has defined for you that X means the vector of decision variables, remember that it no longer means the state of the system. In nonlinear systems, we also often call the state of the system X. So that just keep in mind your context and how the writers of whatever you're looking at, if you're looking at an optimization book or you're looking at an optimization software or you're looking at a nonlinear systems book, how they define X, and then to just remind yourself of that when you're reading that certain source so that you don't get confused, because this clearly this is not the state. And a lot of times what we'll do in optimization-based control is we're actually going to use X to represent the decision variables of the controller, which because the controller computes inputs, X in some of the programs we write might actually mean input to the process, which is different from how we would ever write that like in an undergrad class, where we would say like X is the state, Y is the output, U is the input. But in optimization like software, you may not have the flexibility to necessarily always choose what variables that software designates as sort of the built-in decision variable. So that's just something to keep in mind. F is going to be the objective function. This does need to be scalar. It's a scalar function of x to maximize or minimize. Ci here is a constraint function. So these will be like equality and inequality, equalities and inequalities that x has to satisfy. So as an example, there will be something like, here's some notation again from this book. So it's good to know the notation of whatever you're reading. So there will be something like this, that's like some function, again, x being a decision variable. And they use this to represent the number of equality constraints. So E would be like maybe 1, 2, 3, 4, if you have 4 equality constraints. And then here it says I is in the set of inequality constraints. So this might be like the indexes 5 and 6 correspond to your inequality constraints or something. And you will minimize over your variable contained in r to the n f of x such that these things are true. So it will say, here's x, you might have bounds here, but here's your constraints, your bounds on your decision variables, and your objective function. So let's look at an example. I'll put that on the next page for room. So here is an example. We want to minimize x1 minus 2 squared plus x2 minus 1 squared such that x1 squared minus x2 is less than or equal to 0, and x1 plus x2 is less than or equal to 0. So this here, in terms of the notation we defined on the prior slide, this is what we're going to call f of x. This is the objective function. x1 and x2 are decision variables, not states. And then our c of x here is going to be negative x1 squared plus x2 and minus x1 minus x2 plus 2. So a valid question here is to say, like, okay, why did I flip the negative over here? So that when I wrote it over here, it was negative x1 squared plus x2. And again, like, oh, sorry, this says 2. This should be 2. Sorry about that. And then like negative x1 minus x2 plus 2, like, why did I move this to the other side? And so the reason is because in this book, they're defining that the equality constraints need to equal 0 and the inequalities have to be some number that's greater than or equal to 0. This type of way of thinking of like, okay, the way I'm going to write the constraints is one way and one way only, is very consistent with optimization software. Like if you go use fmincon in MATLAB, you will also see that they require that you put in your inequality constraints in a way that I believe that one is less than or equal to 0. So just thinking of it in terms of like your constraints are only going to be one way is very important for then being ready to like look at what is the way that like the software you're using defines it and how do you put it in. So in this case, we're going to say, okay, here's if this is what I'm requiring. If this is what I'm requiring, that my inequality constraints are greater than or equal to 0, then I do have to move everything to be in terms of that. So this is like 2 minus x1 minus x2 is going to be on the side where it's greater than or equal to 0, because then this will say 0 is less than or equal to that, so this is greater than or equal to 0, etc. So now we're going to draw our feasible region. So here's our parabola. So this is the part where x1 squared is equal to x2. So this is going to be the parabola generated by this, or like that represents what this constraint says. And then you would say like, okay, everything where x1 squared is less than or equal to x2. So that would be like this part. Oh, sorry. No, I did that wrong. Darn. The other way around. This is x1 squared is less than or equal to x2. So here's x1 and here's x2. And so the set of decision variables that would satisfy this would be the ones that are in this region where x2 is essentially greater than or equal to x1 squared. So it's above this. So that's the first constraint. Now we're going to have a second constraint, and so it's this one. So it says x1 plus x2 is less than or equal to 2. So that's going to be a line, because that's a linear type constraint. And so it's going to be points underneath this, so where it's less than or equal to 2. So now let's combine those two. We can put this one together with this one. And here we have x1, we have x2, and then we said that like essentially over here and under the curve, or sorry, over here and above the parabola. So to the left of the line and above the parabola is where both of those are true. So this is actually the feasible region, because this is the region where all the constraints are met at once. So here's our feasible region. So our okay values of our decision variables are ones that are in here. If it's outside of here, it's not okay to choose those because they wouldn't meet your constraints. So it'd be like, that would be the same idea as someone saying like, oh, I'm willing to spend, my budget is whatever, $5,000. And you say, well, I found you that you can, whatever, you can get a more fun trip if you spend $5,500. And it's like, okay, well, I said my budget's $5,000. So I'm not going to buy the more expensive trip, even if you tell me it's better, because my budget is this much. I'm saying optimize within my budget. That's the like idea of this. So then if you have these contours of f over here that we're going to make, so here there's a function f, and this is actually, as you can see, it's a circle. So it's centered over here at like 2, 1. But depending on what x1 and depending on the value of f of x, so I could say this circle is equal to 5. I could say the circle is equal to 10. And depending on that, the circles get bigger and bigger. And the bigger the circle, the larger the value of f, meaning the larger your objective function. Since we're trying to minimize it, what we want is the value of x1 and x2 that make this as small as possible within the feasible region. So you can see that that point is actually right here, that if we keep drawing these circles, that here is a larger like circle than here, for example. So until you get to this one, this is the smallest circle you're going to get, the one that goes through this point. That's the smallest circle you're going to get that goes through the feasible region, because this is the edge of the feasible region here. So this is actually the optimal solution of the optimization problem, which I'll call x star. That's the optimal values of the decision variables, whatever numbers they are over here. And then, and these are the contours of your objective function. So this is actually, we're really lucky for this problem that it's able to be plotted like this, that we can actually see it. But yeah, that makes it easy to see what's going on. So contours of f are the set of points where f has a constant value. And the feasible region is the set of all points satisfying all the constraints. So it's the area between the two constraints here, but in general, it will be whatever set of x1 and x2 satisfy all constraints. So it's really a set. And then we have this solution. And then everywhere else that's not in the feasible region is infeasible. So another important thing is that if you maximize f is equivalent to, or will give you an equivalent solution in terms of x1 and x2, minimize negative f. So clearly, like, these objective functions are different, right? One is positive, one is negative, but it gives the same decision variables. So some other things that, for the sake of time here, I'll just sort of say them, is linear programming refers to a certain class of optimization problems that have specific types of objective functions and constraints. So this would, let's come back. Oh, that was something else. Let's go back to this example. The number of units that you sell. Now, you can't sell half a unit, maybe. Like if you're selling like a box of chocolate, maybe you're like, I can't sell half a box of chocolate. I need to sell either the full box or I don't sell the box. In that case, these are integer decision variables because now they can only be discrete numbers. Like they can be 1, 2, 3, 4, 5, 6, but they cannot be like 1.5 or 1.1. Search every single value of like x1 and x2 within these bounds that satisfy this. Now for this case, if these are integers, it's very easy to enumerate the cases, right? To say like 3, 4, and 5 are my only values, 0, 1, and 1 are my other values of this. I can literally say like that's 6 choices or something. I'll plug in all 6 choices, look at the value of this objective function, search through it like as if I was going through like a list and say which one of those is the smallest and then choose, or the largest or whatever, and choose that one. But in general, like problems like this, it's not that easy, right? Because here x1 and x2, they vary continuously. So you don't want to have to do that. You don't want to have to just lay out every single possible number. I mean, how can you even do that? But even if you take advantage of continuity of these functions and you're still just trying to do a brute force search over every else. And so a function f is a convex function if its domain S is a convex set, and if for any 2 points x and y in S, the following property is satisfied. F of alpha x plus 1 minus alpha y is less than or equal to alpha f of x plus 1 minus alpha f of y for all alpha in 0 and 1. So then you have strict convexity if this holds without the equality. And then, so convex optimization is important because if you have a convex optimization problem, there actually is only one solution. So if you find the local solution, you found the global. So if the objective function and feasible region are both convex, then any local solution is also a global solution. And so this means that if you get algorithms that work for this class, and if you're able to transform your problems into this class, that you actually get a lot of power then in being able to use those algorithms. Because when you find the solution, you don't have to sit there and be like, oh, is it really like the real optimum? Like you can say it found the local min, that's also global min. So that's kind of powerful. So convex optimization, people really like that one. So you have a convex program is constrained optimization where your objective function is convex. Where you have equality constraint functions are linear. So if you have equality constraints, they are linear, not only convex, but linear. And the inequality constraints are concave. So a few final points here. Optimization algorithms are iterative. So the way that algorithms for optimization work, you start with an initial guess of what your decision variables should be. So if we had this problem, the way an optimization algorithm would solve it, you would make an initial guess of x1 and x2. That is not the same as initial conditions. Initial conditions for differential equations are something like about the physics, like that is the place where the states of the system start. For an optimization algorithm, there's only one solution. It's not an evolving dynamic system. It's like you want to know what are the values of certain variables that make the system, or sorry, that make the optimization problem have a minimum objective function subject to the constraints. So when you have this, you make a guess of what x1 and x2 might make this objective function minimum subject to the constraints, and then the algorithm improves on that. And the way that it does that is by guessing a new value and trying it out, and then it like analyzes some properties, like it might look at the gradient in some way of the objective function, or how much did it decrease compared to the prior objective function, how close is it to meeting the optimality conditions, and then it guesses a new guess and keeps going until it finally meets some stopping criterion, often based on optimality conditions. And then, but the way that it goes from iteration to iteration, the way that it updates the guesses is how algorithms are different from one another. And it turns out that the way that it updates the guesses actually plays a huge role in whether or not you get solutions. And so a good algorithm should be, ideally should be robust. So it should perform well in a variety of problems in its class. Like if it's convex, should perform well for many convex problems, not just for like one that you want to do today. For many different values of initial guesses. It should be efficient, ideally. It should not take excessive computer time or storage. It should be accurate, ideally, so able to identify a solution with precision, not be overly sensitive to there being errors in the data or to rounding errors on a computer. But a lot of times there's trade-offs between all these different objectives or goals. So we need theory to understand, like, how can we design algorithms that make sense to tell me whether or not I really found the solution, and then and to also analyze the convergence of whether or not you're going to get a solution and under what conditions does this iterative strategy actually go to a solution. And then we also need to know the algorithms to be able to be experts in this field. So optimization is often called mathematical programming. That's because it started really before programming on computers became like a big, before that term was big for computers. So that's why it's confusing. Okay, then that is the end of our lecture here.